In this video, we're going to once again compute confidence intervals for a two-way ANOVA with repeated measures on one variable. We'll use the Chow data again, ortho K, but we're going to analyze with the mixed procedure in SPSS using a maximum likelihood estimation. Notice we have now put the data into a vertical format because it has to be up and down. No longer are there years across here. We have years, 0, and then down to 1, 2, 3, 4. And so we're going to split our data again by I just to be consistent with the other one. We actually wouldn't need to do that here. We could measure I separately, but we're going to compare groups by I. And then analyze, mixed, linear, ID. Repeated measure is year. And we're going to do compound symmetry. There are probably better covariance structures than compound symmetry, but we'll get to those in a later session. Our dependent variable now, instead of all those AL 0 through 6, is just going to be AL. Our factor is going to be lens type 2 and year. And we're going to use spherical equivalent as a covariate so that we can get everybody in the same place on the first year. So let's see. So our model is lens type by year and spherical equivalent. And we want to get these means. And that looks like it's about it for statistics. I guess we should look at the parameter estimates since we have statistics, parameter estimates, so we can get the spherical equivalent. Notice spherical equivalent sphere is not the same thing. The other one we did sphere, this one we have spherical equivalent, so we're going to use it. Okay. We see we have 188 total subjects, compound symmetry. We have our fixed effects. Everything's significant. Here's our parameter estimates. Here's our covariance table. Now, before we had to collect the whole analysis of variance source table in order to get our mean square error. Here we use the estimates of the covariance parameters. And have it for the left and right eye. We also want to get our means. Lens type by year, copy. Notice these have been these little letters in here. It's because it's the least square means that have been adjusted for the various spherical equivalents. So we need to first, or well, I don't know first, but we need to get rid of these letters because it won't work. Our graph will have trouble with those letters in there. There we go. All right. Now, again, we want to look at the simple effects. Let's copy in our do our graph. Insert a spheric and spheric no growth x values y values, the means, and spheric growth, x value the years, y values the means. Okay, and let's add a legend so we can keep them straight. Okay, you can see when we adjust for spherical equivalent, we get a little bit of closer relationship down there. Okay, now let's calculate our error bars. Again, we want to go this way. If we wanted to go this way, going across and comparing, say, year 0 baseline to year 5, we would just use the estimate of the CS diagonal offset. We would take the square root of that to get the standard deviation, and standard deviation divided by the square root of n to get the standard error. But we still have this problem whereas these measures are not within subjects, so we have to add in the between subjects variance. Now, this is a little non-intuitive, but the way you do that is so the mean square, well, the sums of square, set, well, it's not really sums of square. What we do is we're going to take this value plus this value. And we're going to multiply that second one times the number of years, which is 6. And that gives you the sums of squares. Now we want to we want the end, so let's come over here to our last one and just copy down our ends. Cheat a little. It's not really cheating, but okay. So we have sums of squares, we need the mean square. So the sums of squares, actually, I'm going to take that back. In this model, adding those two together gives us our equivalent to the equivalent to the mean square cell. The way we've taken the offset plus 6 times the covariance, the diagonal, gives us this number. And that actually is our equivalent to mean square error. Now we want to get, well, and then the standard deviation equals square root of that number. That's the standard deviation. And equals this, fix it with F4, divided by the square root of n, gives us our SE. And then our T. Now we have 3 comparisons, so we can go A, B, A, C, B, C. So that's 3 possible comparisons. So that's a Bonferroni, 0.16 is our 84%, but we're going to divide that to make it a Bonferroni correction by 3. And the degrees of freedom are n minus 1. Notice how close that is. It rounds to 1.96, so it's an 84% confidence interval with 3 groups is essentially the same as a 0.05 rejection. So equals T times SE is our 84% CI simple between subjects variable, or confidence interval. So let's come down here, copy all these guys, and then go in here, design, add a chart element, error bars, more error bar options, custom, specify values. These guys. Okay. And then we'll go to this one. Design, add a chart element, error bars, custom, specify values. 42s. And then finally we get the grower guy here. oops, okay, the grower guy. And design, add, error, more, error, more, custom, specify, 52s. Again, these are bigger down here because there's fewer values. And then get rid of these annoying horizontal lines. There's our graph. This makes more sense because they start out, we've adjusted, so they start out similar, and then at least by the 4th year, everybody's different, or the growers are different from the others. The aspheric and spheric, some of those subjects are pretty much the same. We'll cover the differences between the spheric groups when we look at logistic regression. Okay, so that's it. When we want to look at the effect size, we're going to look at, let's see, this one was, that's the aspheric, minus, I don't know, I don't want to do it the other way, but it does, whoops, doesn't really matter, divided by the standard deviation. Okay. Put those in the right spot. And before we got a half a standard deviation difference, now we get 0.06, which is trivial. All right, so that is how we calculate confidence intervals to get point estimates and effect size to get an idea of clinical relevance. If we come back here, let's go ahead and copy this. I don't know, let's look at equals this. No. Let's look at 5 years of aspheric minus 5 years of growth divided by standard deviation. And we get an effect size of 0.9, almost a whole standard deviation difference. That's a pretty big effect. All right, that's it.